Let's return to the casino for some more probabilistic intuition. Recall that we framed our understanding of probability in terms of experiments, artificial experiments like tossing a coin and throwing a dart at a dartboard. We considered events like tossing a coin 4 times and getting an outcome like heads, tails, heads, heads. We considered throwing a dart at a dartboard and landing somewhere in the middle. Those are outcomes, which are elements of our probability space. But are those really the things that we're measuring? In a real-world situation, we're going to measure some numerical quantities. In the coin tossing example, we might be measuring x equals the number of heads. In this outcome, it's 3. In the second example, we're probably most interested in r equals the distance from the center. So here, r was equal to 0.15, and here, x was equal to 3. Such measurements are given the old world term random variables. But we see what they actually are functions from the sample space to the real line. And that is what we will be spending most of this year studying. We now have a rigorous arena in which to do probability theory, that is, a probability space, an abstract sample space equipped with a sigma field of subsets and a probability measure on that sigma field. We spent a lot of time constructing specific ones, for example on the real line, and those will be relevant to our studies of random variables. But it's important to understand that in probability theory, usually the probability space is in the background. It is, in a word, inaccessible. We actually don't know much about the modeling probability space. We can only derive things about measurements that we take in experiments. And so most of the time, random variables will provide most of the information that we can actually get. A random variable in this model is a function from the sample space to some other set, which is called the state space. Most of the time, that will be the real line for us. It could be the complex plane. We can consider complex valued random variables. It could be Euclidean space of dimension d. Usually we would call random variables taking values in Rd random vectors. It could be an infinite dimensional Hilbert space or something else. We should keep an open mind. Now, with this setup, we should really call these things random functions. But the term random variables has stuck for over 200 years since it was first introduced by Laplace in his treatise on probability in the early 19th century, and it may be even older. But let's be careful. Not any old function will do. Looking again at our experiments, we are measuring the values of the random variables. So we need events like x equals 3 and r equals 0.15 to be the sorts of things we can take probabilities of. Now, in the discrete example of tossing a coin, x equals 3 is something that we know is going to have positive probability. But in the dartboard example, the chance of landing exactly 0.15 units away from the center, precisely with no room for error, is, as you would expect, 0. So we need to be a little more generous about the kinds of measurements we're going to make. We really need to be able to measure things like what is the probability that x is less than or equal to 3, or say x is greater than or equal to 2. And we need to be able to measure the probability that r is less than or equal to 0.25. Those are the sort of measurements that make sense in a game of darts anyway. We need to be able to measure the probabilities of events like that. But it's not guaranteed that such a subset of omega will be measurable. So we have to insist on that. Now, just to be clear on notation here, this event means the set of all points, omega, all outcomes, in the sample space omega, for which the function's value, x of omega, is less than or equal to 1. A random variable, properly speaking, is a function from the sample space to the reals with the property that all of those events, the event that x is less than or equal to t for any real number t, is in the sigma field, is measurable. We'll soon see that if all of those sets are measurable, many others are as well, and our understanding of measure theory will come into play here. But since we know we have these ones at least, let's circle back to cumulative distribution functions. In fact, every random variable will have a CDF. Here's what I mean by that. Start with a random variable, that means a function from the sample space into the real line, and for each real number t, consider the event that x is less than or equal to t. That is by definition measurable, which means we can calculate its probability. And so that gives us a function. Fx of t is the probability that x is less than or equal to t. Again, this means the probability of the event, the set of all outcomes in which x of omega is less than or equal to t. But that looks just like our definition of the CDF of a radon measure. And in fact, we'll see in a moment that it is. But for now, let's just check that this function from reals to reals does in fact satisfy all of the conditions of a CDF. It is non-decreasing, right continuous, and has the correct limits at plus and minus infinity. So for non-decreasing, if I have two real numbers, s less than or equal to t, and I look at the events that the random variable x is less than or equal to s, and the event that x is less than or equal to t, well, because t is larger than s, if x is less than s, then it will also be less than t. That means we have a containment of these two sets. And therefore, by monotonicity of probability measures, the probability that x is less than or equal to s will be less than or equal to the probability that x is less than or equal to t. But the right-hand side is fx of t, and the left-hand side is fx of s. So we have monotonicity. Now for right continuity, we'll be slightly vague here. If Tn is a sequence of real numbers that decreases to a real number t, then the sequence of events that x is less than or equal to Tn decreases to the event that x is less than or equal to t. That is to say that the event that x is less than or equal to t is the intersection of the events that x is less than or equal to Tn. Now that claim might seem like it requires some sort of continuity of the function x, but it doesn't. And in the next lecture, we'll get into the particulars of statements like this. For now, let's take it on faith. Thus, by the continuity of probability measures from the beginning of the last lecture, the probability that x is less than or equal to Tn decreases to the probability that x is less than or equal to t. And since this is fx of Tn, and this is fx of t, that limit is exactly the statement, given that this is a decreasing sequence, that fx is right continuous. And for the limits at plus and minus infinity, we just note that if Tn is a sequence that decreases to minus infinity, then the event that x is less than or equal to Tn decreases to the empty set. There is no outcome in which x of that outcome is less than or equal to every real number, because the variable x is real valued. And so whatever values it takes, they must be in the real line. And that means, again, by the continuity of the probability measure, that the probability that x is less than or equal to Tn decreases to 0. And so that gives us the limit of fx of Tn being 0. And similarly, if Tn goes up to plus infinity, then the event that x is less than or equal to Tn will increase to the entire sample space, since x is real valued. And so that shows us that in this case, fx of Tn, which is the probability that x is less than or equal to Tn, increases to the probability of the whole sample space, which is 1. Thus, this function here, determined by the random variable x, is a CDF. That means that it is the CDF of a unique Borel probability measure on the real line. We call that probability measure μx. It is the probability distribution of x. Now remember, the probability space, omega fp, is in the background. We don't really have much access to it. So often, this probability measure on the real line is all the information that we will have about our random variable. And actually, in reality, frequently we won't even know that. We will only know certain statistics of this probability measure, certain numerical quantities associated to it that we're going to get into in a moment. But let me just note that right now we've gone through a fairly convoluted process to get there. We start with a random variable x, we produce from it this cumulative distribution function, and then we use this correspondence that we proved that every such function, non-decreasing, right continuous, with limit 0 and 1 at minus and plus infinity, is associated to a unique radon measure, μx. But how do we actually get this from here? How would we calculate it even if we knew x without going through this intermediary step? Well, we'll see that the connection between these is much less convoluted and much more direct in the next lecture. But before we get there, let's talk about expectations. Again, we frequently will not have complete information about the distribution of a random variable, so we can hope to get a snapshot, some information about it, and the minimum information that we hope we can always get is its expected value or expectation. So let's talk about what that means. To motivate this discussion, let's start in a finite probability space, meaning that the sample space is actually a finite set. Now in that case, there's no technical obstruction to taking as the sigma field the set of all subsets, and we can calculate probabilities of any event so long as we know the probability of each individual outcome. In this discrete setting, those will typically not be 0, at least certainly not for all of them. The reason that that's good enough is by the additivity of probability, because all of those individual outcomes as singleton sets are disjoint from each other, and therefore the probability of the event E is actually the sum of the probabilities of all of the individual outcomes in E. And we could write that in a slightly more useful way as the sum over all elements in the sample space of the indicator that omega is in E times the probability of the singleton omega. So just to be clear on notation here, this indicator function is a 0, 1 valued function defined on any set, and its value at some particular point omega is equal to 1 if omega is in A, and 0 if omega is not in A. We will use indicator functions frequently throughout this course. Now, in this finite setting, if we have a random variable defined on this finite set omega, we can calculate its cumulative distribution function in a similar way. We want to calculate the probability of this event, which means the probability of the set of all omega for which x of omega is less than or equal to t. And following exactly the mold we did above, we can write that as the sum over all points in omega of the indicator function that x of omega is less than or equal to t times the probability of the singleton omega. So in both of these cases, we can write the probability involved as a sum over the whole sample space weighted by the probabilities of some function. Now that function is a 0-1 function in those cases. But if we want to combine all of this information together into one number that tells us something about the distribution, then what we can do instead is write exactly such a sum, and instead of putting zeros and ones here, we put the function values. Simply the sum over all points in the sample space of x of omega times the probability of omega occurring. This is the weighted average of all possible values of the random variable, weighted according to the probability that that outcome occurs. And we'll make that characterization of this precise on the next slide. But let's look at one simple example right now. Again, tossing a coin. To save time, I've only tossed it 3 times now. There are 8 possible outcomes when I toss a coin 3 times. And each of them has probability 1/8. Now, let's consider our random variable x, the number of heads. Here we can write the values corresponding to each outcome. We have 3, 2, 2, 2, 1, 1, 1, and 0. And that means that this weighted average, which we write as Blackboard bold E, expectation, will be 3/8 plus 2/8 plus 2/8, and so on down the line. We can write that as 1/8 of 3 plus 3 times 2 plus 3 times 1 plus 0. And that is equal to 3/2, 1.5. Now, of course, 1.5 is not in the range of the function x. X never takes non-integer values. But this number does tell us something about the values that x might take. We know that x can take values 0, 1, 2, and 3, and 1.5 is right in the middle of that range. And indeed, what this calculation shows is that weighted according to the uniform probabilities of all of the outcomes, the average value is in the middle of the range, 1.5. Now, of course, we're going to build up to the first major theorem of this course, the law of large numbers, which will tell us that what's really going on here is that if I keep repeating this experiment over and over again, tossing the coin 3 times and writing down the number of heads that came up, and take the long time running average of all of those numbers, I will get closer and closer to this weighted average. But we'll get there. Thus, in the discrete setting, this weighted average definition of expected value is perfectly reasonable and tells us something meaningful about the distribution of x without actually calculating the distribution of x. It's also perfectly fine if we have a countable sample space. But problems arise if we're in the continuous setting where, as we've seen, it may well be true that the probability of any particular outcome is always 0, even though the probability of lots of events, of outcomes, is positive. So how do we deal with that situation? Well, in undergraduate probability, the solution is to recast this weighted average in a different way. Instead of summing over the outcomes, we can sum over the possible values. Indeed, if we sum over all possible values t, and note the actual set of values that x takes is finite, so this is still a finite sum, and then sum over all of those outcomes for which x of that outcome is equal to t, then that is a way to break up this sum. So we can rewrite the terms in the sum. But inside this sum, this is always equal to t. So we can pull that t out. And now we note that this inside sum, the sum of the probability of the singleton omega over the set where x of omega is equal to t, again by the finite additivity of probability, is nothing other than the probability that x equals t. And there we have our alternate formula for expectation in this discrete setting. Now in undergraduate probability, what you do is to find an integral analog of this in the continuous setting. But one needs some technicalities in order to even make sense of that. And this approach, even when it works, which is not all the time, as we'll see, there are many problems. In particular, one nearly immediate fact from the original definition of expected value in this discrete setting is that it is a linear functional. If I have two random variables, then the expected value of their sum is the sum of the expected values. That is actually pretty hard to see from this definition. In fact, seeing it directly from here without going back to here requires, in the undergraduate probability case, understanding joint distributions of random variables, which is much more sophisticated than is needed to see such a basic property. So that's why we're certainly not going to be trying to follow this approach. Instead, to go from the finite or countable discrete setting to a more general setting, we're going to recast what this thing is, and we're going to see that it is actually an integral already. It is the Lebesgue integral of x with respect to the probability measure p. And so that will be our goal after understanding some of the basics of random variables, is understanding how to integrate them.